Everyone, welcome back, and we are going to do our solutions to exam 3 for ENGR045. So let's go ahead and get started. So I received the technical memo. I've got these values of E0, of E. What are the standard conditions for electrochemical cells? List them out quantitatively. So if we're at standard conditions, i.e. E0, we need to make sure what is our temperature is equal to 298 K. We need to know that our basically molar quantities are equal to 1 molar, and we are at basically atmospheric pressure, 1 atm. So there we go. Any mistakes in the calculation of E0? Well, let's figure it out. So let's go ahead and we'll pull up Mathematica. Let's actually, first off, let's delete, let's close this. Don't save. Let's pull up another version. Let's open up a notebook. Let's go to quit the kernel locally, and then so let's system. So we're looking at cobalt. We are looking at PB, we're looking at Mg, we're looking at nickel, CD, and S10. And at the same, so cobalt, PB, PT, PT, Mg, Ni, CD, Mg, SN, CD, PM. All right, perfect. Okay, so I think we're good. So now let's go to our lecture notes here and let's find these values. So let's go ahead and pull these out. So our standard, again, these are only for standard conditions. Once we are not standard, then these don't work. So let's look for cobalt, which is going to be minus 0.277. My PB, as we can see here, is going to be minus 0.126. I don't want to do a double sign here. My PT is going to be equal to 1.2. My Mg is going to be very negative because it's not very electronegative. Minus 2.363 wants to give up electrons. My nickel, minus 0.250. And then CD, cadmium, minus 0.403. And then finally my tin is going to be equal to minus 0.136. So we can now basically double check all those values. So remember, whenever we're doing, let's get enter. So again, it's the cathode minus the anode is going to be my E0. So I'm just going to do a table. So actually, I'm just going to go see. So my cathode, again, typically the way we're looking at the cathode material is what? So in our traditional, the cathode is at our positive terminal, but let's see if that's actually the case. So, so we're going to go PB minus CO. There's a mistake there. So again, that kind of makes sense too, because look at PB and CO. So CO is much more electronegative, or much less electronegative, and actually we can kind of double check this on our, let's go back and let's look at our good old friendly, let's look at our files. Let's go ahead and look at our periodic table, and we could just confirm this ourselves just for this first one so that we know what we're doing. So PB, and so if I look at these values, you could look at basically electronegativity on the other chart. So we could see here electronegativity is the second one, so this 1.91 here. So if I look at PB and CO, so let's look at CO, so that's 1.88. Let's look at, where's my lead? Remember, 1.88, and my lead, my PB, is 1.8. So CO is more electronegative, so I just want to grab those electrons, so that should be the value that we look in here. So let's go back to our question. Let's finish up our answers. So PB minus CO, Mg minus PT, yes, that better be negative. So again, we're seeing some CD minus Ni, Sn minus Mg, and PB minus Sn. Oops, not PG, PB. So let's just double check that. So there's some correct values here, but there are other ones that are incorrect. And again, that'll be what we'll see here. All right, so now once we are measuring these once we start to measure these actual E values, so in our condition, we need to place an X on the material that oxidizes. based on these values here. So these values tell you where the electrons are going. Remember, if it's positive, the electrons are flowing from where? Well, they are going to flow from my negative terminal to my positive terminal. The anode is going to, again, basically oxidize at the, and is going to give up electrons. Cathode is going to steal those electrons. So where are electrons being given up? So we'll see where the electrons flow. So let's first start seeing with here. So here, the electrons are flowing, if we're looking at E, from here to here. We look at this direction. So based on these values, again, at non-standard conditions, here they're flowing from here to here. Here they're flowing from here to here to here, and then the other way here. So which material is oxidizing? So the material that oxidizes is the one that gives away the, basically, again, looking back here, material that oxidizes is the one that gives away the electrons. So this one's oxidizing, ox. Y, the material that will reduce, so that'd be the opposite, Y. So we got that. Done. The full cell reaction for the nickel and cadmium so if I look at nickel and cadmium here, so it looks like nickel is giving away, so nickel is reducing to Ni2 plus 2E minus, and then my cadmium is going from CD2 plus 2E minus goes to CD. I'm going to add up the reactants and the products, so on both sides of the reaction, so this will give me nickel plus CD2 plus goes to CD plus nickel 2 plus. Here we go. We've got it. Place a circle on which, again, this could be, you can answer it either way for these reactions, but again, we're looking at it. Place a circle on the material that will corrode in the non-standard conditions. Again, that's the same thing for, your X's. So the X's are going to be the ones that corrode. So circle corresponds to X in the non-standard conditions. You could also answer this question for the standard conditions as well. Again, we're looking at the same values. And now, finally, the experiments were conducted at an anode concentration of 0.35 molar and a cathode concentration of 0.75. What was the temperature for this experiment for the nickel cadmium? So now we need to use our Nernst equation, which is E, what we measure, minus E naught equals, and we could just pull up our notes just real quickly, make sure that we're good to do. So you can see here, where is our good old friend, the Nernst equation? So we've got the Nernst equation right here, minus RT, so let's go ahead, minus RT, let's go put it over here, over NF. And here's the number of electrons. 2, R is our gas constant, T is our temperature, F is going to be our Faraday's constant, 96485, I believe, but we'll double check that. And it's the log of what? So if I look at this here, I'm always looking at these ones. So in this expression, is the CD my anode or my cathode material? So it's always, this is my, basically, this is reactants, this is products. So it's always the concentration of this is my anode material. So anode over cathode. So there we go. So now we can go ahead and start to solve and figure out what temperature was conducted at this experiment. So all I'm going to do is my E naught is going to be equal to, basically, for this experiment, what did we have it as? This is my nickel cadmium. So my CD minus Ni. So that is my E naught. My, again, N equals 2. My R equals 3.814, or 8.314. 8.314 joules per mole K. My temperature is an unknown. And my F, Faraday's constant, let's go ahead and look at that. I think it's 96485. We'll look at it. We'll make sure. Come on. We need to get Faraday's constant. Yep, 96485. See, the memory's still there, but I want to make sure that 96485, you could do unit analysis, make sure that's the case. So let's go ahead and solve that. And then my E is going to be equal to, what did we measure here? My E was, for nickel cadmium, 2.4. So 2.4. So let's see what the temperature was for this experiment. E minus E naught set equal to R times T divided by N times F. Again, this is probably unnecessary. And I'm going to do the log times log of basically my concentration of my anode over the concentration of my cathode. So anode was 0.35 divided by 0.75, and then solve. That's a pretty insane temperature, but that's what it is. So now on to question 2, and then let's keep going with this practice exam. Thanks. I'll see you in the next video.